These are the answers for Worksheet 15.1, series and parallel circuits. Okay, let's go through the answers. We have a series circuit here, right? The current flowing in the circuit is I. The total potential difference in the circuit is equal to the sum of the individual potential differences, all right? So in other words, I can write it this way. The EMF is equal to V1 plus V2 plus V3. Okay, because there are three components here, all right? Effective resistance will be given by the sum of all the resistances. So R1 plus R2 plus R3. Okay? Then for parallel circuit, the EMF of the circuit is equal to the PD, right, across each component. In other words, the EMF is equal to V1, V2, and V3 if you label the PD of each branch to be V1, V2, V3, all right? So, okay, let's go on. The current flowing in the circuit is equal to the sum of individual currents in each branch, I1, I2, I3. So I can write it as I is equal to I1 plus I2 plus I3. Okay? Effective resistance, 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3. All right? Depending on the number of branches there are. All right, effective resistance here, very straightforward, just add them up. Okay, but just to show the working, right, let me be stricter with myself and write the decimals. So 1 plus 5 plus 12 is 18 ohms, 2 SF, so you can leave it as it is. Part B, there's a trick here. This is actually a short circuit. Right, so effectively what happens here is that the current will bypass the 3 ohm resistor and it will be completely ignored. All right, the current will move through the path of lower resistance. In this case, the wire has no resistance theoretically, so the current will not pass through the 3 ohm resistor at all. So the effective resistance is just the sum of the two ohm resistors, right, which gives you 4 ohms. Okay, all right, next, to find the effective resistance here, 1 over R is equal to 2, so R will be, okay, this pen is not cooperating, so effective resistance will be 1 over 2. Right, so which is 0.5 ohms. Okay, 2SF. All right, then for the next one, 1 over R equal to 1 over 3 plus 1 over 1. So it's actually 4 over 3, right? So our effective resistance will be 3 over 4. You flip it. Okay, flip 4 over 3, you get 3 over 4, so 0.75 ohms. Okay, for part E, this is a short circuit, right? So actually the effective resistance is 0 straight away. Okay, you don't need to actually do any working for this, right? But if you want to do working, this is how it will look like. Right, effective resistance 1 over R is equal to 1 over 10 plus 1 over 0, and we know that 1 over 0 is actually infinity, right? So if 1 over R is 1 over infinity, 1 over infinity means let me see, 1 over 0 is infinity. Okay, yeah, sorry. So 1 over 0 is infinity. So 1 over R is infinity, right? So therefore R is equal to 1 over infinity. If 1 is divided by infinity, you get 0, right? So if you want to show working, this is how you look like lah. But it's not necessary. Okay, once you have, by the way, it's 2SF. So I should write 2SF over here. Okay, so 2SF, 0.0 ohms. But it's not necessary to write the working here, right? Once you know that it's a short circuit, effectively it is 0 ohms already. Okay, for part F, don't be tricked by the shape of the circuit. Don't be tricked by the shape. It can be a triangle, it can be a rectangle, it doesn't matter. What basically matters is that there are two branches, one branch over here and the second branch over here, right? So when there are two branches in parallel, we use the parallel formula, so 1 over, the upper branch has 2 ohms and 2 ohms in series with each other, which means that the upper branch has a resistance of 4 ohms and the lower branch has a resistance of 2 ohms, right? So the upper branch, the two 2 ohm resistors are in series with each other. So the total resistance for the upper branch is 4 ohms, right? Then you get 3/4, right? 3/4, 1 over R is 3/4, therefore R is equal to 4 over 3, which is 1.33333 to 2SF will be 1.3 ohms. Okay, question 4. Right, we are told that there's a resistor and 2 similar light bulbs. Okay, that's important, similar light bulbs. That means that the resistance of each of these light bulbs are the same. They are connected in series to EMF 6 volts. All right, so determine the resistance of the resistor. Now, we cannot do it directly because we do not know the potential difference across R. All right, we cannot take 6 divided by 0.15 because that will give us the total resistance of the whole circuit. But we do not know the resistance of the two bulbs, so we can't do it that method. So what we need to do is to find the potential difference across the resistor R first. All right, and we know that in a series circuit, V equal to V1 plus V2. So the potential difference across the resistor R, right? Maybe I'll write it out. PD across resistor R is equal to the EMF 6.0 minus the potential differences of the two bulbs, right? Which will give you 3 volts. Okay, so once we know that this is 3 volts, right, then we can find the resistance of R. So R is equal to V over I. You get 3 divided by the current that's flowing across the whole circuit. So I is constant in a series circuit. You can use 0.15. Okay, so we get 20 ohms. Okay, so you got to take note that you cannot take the 6 volts here to divide by the you cannot take 6 volts divide by the current 0.15 to get the resistance of resistor R. Okay, because if you take 6 divide by current, you're finding the total resistance in the circuit. All right, and that is actually what you can do now, right? So when you want to find the effective resistance, you can take the total EMF divided by the total current. Okay, so total EMF is 6 volts and the current is 0.15. So your total resistance will be 40 ohms. Okay. So actually, you can, if the question goes on to ask you to find the resistance of the light bulbs, you can actually straight away tell over here because the total EMF, the effective resistance, is 40 ohms. So R is 20 ohms. So each of these bulbs will be 20, okay, because 40 minus 20 is 20, right? So 20 divided by 2 is 10 ohms each. Okay, so you can actually find the resistance of the bulbs that way. All right, C part 1, state the potential difference across each of the light bulbs. Resistance, the resistor is removed, okay, and replaced by a copper wire. So if the resistor is removed, all right, we are left with just the cell with 2 light bulbs, okay. So effectively the circuit will be like this now, all right. And just now, as I've said, we know that the resistance of the bulbs are 10 ohms each, right? This information, you probably will need it now. Let me just write it down first, okay. Deduce whether the light bulbs will be brighter, dimmer, or maintain the same brightness as compared to the light bulbs in figure 4.1. So for brightness of bulbs, usually the brightness of bulbs depends on the power. Power, we have not learned yet, but power is equal to PD times current. Okay, power, you're going to learn this later, P equal to VI. But for the moment, you do not need to know this. Okay, for the moment, brightness, you can just consider the potential difference across the bulbs. Okay, so previously, our potential difference across each of the bulbs is 1.5 volts, right? So if the potential difference increases across the bulbs, means that it will be brighter. And if the potential difference decreases, then it will be less bright. So here, since there are only 2 bulbs left, right? And the EMF is 6 volts. Therefore, each of these bulbs will be 3 volts each. Because V1 plus V2 is equal to the EMF, right? So 3 volts. So the brightness will definitely increase because the potential difference across them used to be 1.5 volts, but it's now 3 volts. All right? So, in fact, if you were to calculate the current as well, all right, the current is 6 divided by the resistance of each bulb is 10 ohms, 10 ohms. So if you have 6 divided by 20, okay, you get 0.3 amperes. The current has also increased, okay, as compared to before. So both the PD and the current have increased, okay, but we don't need to consider power, we just need to consider the voltage, the PD across each bulb. So definitely the light bulbs will be brighter. All right. Okay, to provide an explanation, we can just say that the PD across each bulb has increased. All right. To be more specific, from 1.5 volts to 3 volts. Okay. Okay, question 5. The circuit shows a 3 ohm resistor and 6 ohm resistor connected to battery of EMF 6 volts. So this is a parallel circuit. All right. Calculate the current flowing through the 3 ohm resistor. So I is equal to V over R is 6.0 divided by 3.0 is 2.0 amperes. Then the current flowing in the 6 ohm resistor, I equal V over R again. Now is 6 divided by 6. All right. Because V is constant, so you're always using 6 volts. Now it's divided by the 6 ohm, so you get 1.0 amperes. Therefore, the current, main current in the circuit, right? If you want to label it differently, this is I1, this is I2, okay? Then you can call it R1 and R2, okay? V is constant. So I will be equal to I1 plus I2. In the parallel circuit, the main current is equal to the sum of the currents in the branches, right? So you get 2 plus 1 is equal to 3.0 amperes. Okay, question 6. We have EMF, E, potential difference V. All right. So, okay, EMF. Do we know the EMF? Okay, we know that the PD across here is 3 volts. Okay, I'm wondering why my pen cannot write. Okay, let me try and highlight this one. Yeah, okay. So R1, the potential difference across R1 is 3 volts. Oops. Then the potential difference across the parallel part is 2 volts. All right, note that these 2 volts here, right, is the same as V3. So it's also 2 volts here because this part here is parallel. So this part here is parallel, therefore V is constant. So it's 2 volts across there. So since the parallel part is 2 volts and the potential difference across R1 is 3 volts, therefore the EMF will be 3 plus 2 is 5 volts. The current I1, okay, is already given as 2.5 amperes. I2, since you are told that in the second branch is 0.8 amperes, so the first branch, right, I2 must be I1 minus 0.8, so which is 2.5 minus 0.8, okay, which will give you 1.7 amperes, 2 SF, so you can remain as 1.7. V3 is, as I said, V is constant in the parallel circuit, so the potential difference across the second branch is the same as the potential difference across the first branch, so it will be 2.0 volts. All right, we'll move on before this document crashes on me. All right, part B, okay, 12 volts. All right, this is a parallel circuit. Okay, so we have 2 branches here. All right, we know that I4 is 0.6 amperes, and the second branch, the current flowing through it is 1.2 amperes. So the main current in the circuit will be 0.6 plus 1.2, which is 1.8 amperes. Then I4, which is the current flowing in the first branch, is already given as 0.6 amperes. Note that I4 is the same across the first, whether it's R4 or R5, the current flowing across them will be the same, 0.6 amperes. Okay? Then for V5 will be, you need to find the current flowing across it. V equal IR. The current is 0.6 amperes. And the resistance of R5, do we know that? Oh, we don't know that, right? So we can't do it this way. My apologies, you can't do it this way. So you need to use the EMF minus the potential difference across R4, because across the entire branch, right, the voltage will be 12 volts because V is constant, so it will be the same as the EMF, right? So the PD across the entire branch is 12 volts. So V5 must be 12 minus 3, which is 8.0 volts. Okay, I can't write it because okay, I think this is a picture. All right, so 8.0 volts, All right, so next one, V6. V6, basically, as I've said, parallel circuit, V is constant. So V6 is the same as the EMF. right, which is 12 volts. So there's no calculation involved here. All right, we will move on. Question 7. Okay, question 7, we have 24 volts, okay, for this whole circuit. As a circuit, you must identify it, whether it is a series or parallel circuit. Okay, so when you look at this, all right, at one glance, you should recognize that it is a series circuit as a whole, because if I take the potential difference across here, I call it V1, and the potential difference across here, I call it V2, right? You add these two together, you should get 24 volts, because V equals V1 plus V2 in a series circuit. So as a whole, you should recognize that this is a series circuit as a whole, okay? So let's look at each individual question. Determine the effective resistance of A and B connected in parallel. So 1 over R equal to 1/3 plus 1/6, which is half. So therefore R will be equal to, flip half is 2 ohms. Okay, I didn't write REFF because it's not the effective resistance of the whole circuit lah. All right. So for the whole circuit, you just need to, because you already found the whole parallel part to be 2 ohms, right? And this 2 ohms is in series with the 6 ohms. So you just need to add the 2 to the 6, right? So 2 plus 6 is 8 ohms. All right, calculate current that flows through resistor C. So to find the current that flows across resistor C, we are finding the total current in the circuit. Okay, the main current, the total current in the circuit. All right, so the current flowing here will be the same as the current flowing through the resistor C. So once we know the main current in the circuit, we will know the current that flows through resistor C. So I equal V over R, right? So the EMF, total EMF is 24 volts divided by total resistance we have found, all right, to be 8 ohms. So your current is 3 amperes. Find the potential difference across PQ. So PQ, okay, we need to know the current that's coming into PQ. Then you multiply it by the resistance of that parallel part only, okay? Because we only want the potential difference across PQ. So we multiply the current that's coming into PQ, multiplied by the resistance of the whole parallel part, all right? Resistance of the whole parallel part. So VPQ, V equal IR, the current is the main current in the circuit, which we have just found to be 3.0, and the resistance of the parallel part, right? Which one is it? The parallel part alone, only the parallel part, will be this one, right? 2 ohms. Okay, so 2 ohms is 6. You get 6 volts. Okay. Then for finding the potential difference across PR, you can do it in 2 ways. You can take the EMF, which is 24 volts, minus the potential difference across PQ, which is 6.0 volts. Remember, I said at the beginning, right? The VPQ plus VQR, right? VPQ plus VQR, it will be equal to the EMF of 24 volts. So if I want to find VPQ, I just take 24 minus 6 to get 18 volts. All right. Alternatively, I can just use, this is VQR, right? I'm finding VQR. Okay, not PQ. My apologies. VQR. Okay, so VQR will be equal to I times R. The current is the same across the entire circuit, okay, which is 3.0 amperes. and the resistance is for QR alone, right, is 6 ohms. Okay, so you get 18 volts. Right, you notice that both ways will give you the same answer. All right, so there are more than one ways to do it, and you can check your answer by using the other method. All right, okay, calculate the current that flows through resistor A. So now we are going into the individual branches of the parallel part already. So let's call it I1, let's call it I2. Okay, or for simplicity, we just put IA and IB. Okay, so we want to find the current that's flowing through first branch and the current that's flowing through the second branch, right? So you need to have the potential difference across here first, all right, PQ. And you can just take the potential difference across PQ divided by the resistance of that branch to get the current. So IA will be equal to, IA will be equal to VPQ divided by the resistance A. Right? So VPQ is what we have found, 6 volts, divided by the resistance A is 3 ohms. You get 2 amperes. All right? Then for IB, there are two ways to do this again. All right, you can take, again, VPQ divided by resistance of B. All right, you can just get 6.0 over 6.0, which is 1 ampere. Or alternatively, you can take, because it's a parallel circuit, we are going into the parallel circuit. So for parallel circuit, I equal to I1 plus I2, right? So IB is equal to the main current I minus the current flowing in the other branch, which is 2 amperes. So 3 minus 2 is 1 ampere, right? So you should get the same answer. Okay, so either way will do. You can check your answer using the other method. Question 7. Okay, for question 7, you need to ask yourself this question. Is this circuit a series or a parallel circuit as a whole? Okay, is this circuit a series or parallel circuit as a whole? If you are not able to answer that question, you will not be able to get all the parts right. Okay, so this one way to determine whether it is a series or parallel circuit is to flatten the circuit by rearranging everything on the same line. All right, so if I were to start from X, okay, and I follow in a clockwise manner, so from X, okay, let me draw over here, X. From X, it goes to the 2 ampere resistor, which is resistor A, and then it will come to this junction P, right? Junction P, which one of the branches will have resistor B, the other branch will have D, E, F, right? The three resistors D, E, and F. Right, so when you do that, okay, these two branches will come together, right, at junction Q. Okay, right, these two branches will come together at junction Q. So once you draw that, okay, you have the last resistor, which is C, and then it goes back to the power source XY. Right, so when you've drawn this, you will realize that this is actually a series circuit as a whole. All right, because if you put a voltmeter here V1 and a voltmeter here V2, all right, and a voltmeter here V3, when you add them together, it should be equal to the EMF. Right, so as a whole, this circuit is a series circuit, not a parallel circuit. Okay? So let's answer each of the parts here. Okay, calculate the effective resistance of D, E, and F. So they are in the same line, right? So you just add them up, right? 3 plus 2 plus 1 is 6 ohms. Remember to use two significant figures. Then effective resistance of D, E, F, and B. Right, so in other words, the whole parallel part, right, the whole parallel part. So in the first branch, we have a 6 ohm resistor. In the second branch, we also have a 6 ohm resistor. So you get 1/3. So resistance will be, you flip 1/3, you get 3 ohms. Okay, determine the total resistance of the circuit. So now as we have already recognized that this is a series circuit as a whole, so you take the resistance of C plus the resistance of the entire parallel part plus the resistance of A, right, to get the total resistance because it's series as a whole, right? As a whole, it is a series circuit. Okay, so we just add them up together. Once you recognize this, it's pretty easy. Okay, the problem is that sometimes you don't recognize it. So we take A first. A is 2.0 plus the parallel part is 3.0. All right, and the last one is C is 4 ohms, is 9 ohms. All right, determine the potential difference across X, Y. So in other words, we are finding the EMF. We are finding the EMF. Okay, so to find the EMF, V equal to I times R. You take the main current, the current in the main part of the circuit, which is 4 amperes, multiply by the effective resistance of the entire circuit, which you have just found to be 9 ohms. So you get 36 volts. All right. Then part E, calculate current I1. The current I1, okay, now there are two ways to go about doing this. All right. The easiest way is if you have realized that the first branch has a resistance of 6 ohms and the second branch has also got a resistance of 6 ohms. And once you recognize that, actually, it's very easy because you already know that the main current is 2 amperes. So it will be divided into two equal parts, 2 amperes and 2 amperes each. Okay, and your question is done. But I'm going to use the more generic way to answer this question because if in another question, the resistance of the two branches are not the same, then you will still need to calculate it. All right. So I1 and I2, okay, we want the potential difference across PQ divided by the resistance of that branch. So I1 equal to the potential difference across PQ divided by the resistance of that branch. So potential difference across PQ is, oh, do we have that information? We don't, right? Yeah, we don't have the information. So actually, you need to find the potential difference first across PQ, which is rather silly. Okay, so I think we will just keep to what we said earlier, right? That, let me just take a look if the other way is possible. Find potential difference across PQ, and then find the current I1. I mean, you will need to find the potential difference across PQ first, which is not difficult. Okay, to find the potential difference across PQ, you take this 4 amperes, multiply by the resistance of the whole parallel part, right? You can find the potential difference PQ, and using the potential difference PQ, you can divide by the resistance of each branch. You can find the current. Okay, so for For argument's sake, let's just do that, all right? For argument's sake, let's just do that. So find a VPQ first. VPQ is equal to V equal IR. So the current in the main circuit is 4 amperes. And the resistance of the parallel part alone, right? Just the parallel part alone is what we found in part B, which is 3 ohms. So it's 12 volts, right? So current in the first branch will be 12 volts divided by the 6 ohms for the first branch. You get 2 amperes, right? So that is, as we have mentioned, the more longer way to find the answer, right? But alternatively, you can just take I1 is equal to the main current divided by 2, all right, which is 4 amperes divided by 2 is 2.0 amperes, right? Okay, this is definitely the easier way to do it, right? So for I2, similarly, there are more than one ways to do this question. You can take the potential difference across PQ divided by the resistance of the second branch, which will be 12 divided by 6 as well. You get 2.0 amperes. Or, as we have said, we can use I2 equal to main current divided by 2, and you get 2 amperes. Or you can take the main current minus the current in the first branch to get the current in the second branch. All right, so there are 3 ways to do this. Okay, so if I do it the other way, will be I2 equal to I minus I1. Okay, the main current 4 amperes minus the current in the first branch 2 amperes, which I have just found, is 2 amperes. Okay, so there are many ways to do this. All right, then find the potential difference across PQ. Potential difference across PQ. So, I already found it. Yeah, I already found it here. Okay, so potential difference across PQ is already, I already found it. So it's 12 volts. All right, then the potential difference across RS. Okay, RS will be here. Right, we need the current that's flowing across it, which is I2, multiplied by the resistance of this individual resistor. All right, so you take I2 times this 2 ohms. Okay, so I2, we have found that it is 2 amperes. Two amperes multiplied by the resistance of that single resistor E, which is 2 ohms, you get 4 volts.